Hello. Today we're going to discuss the Heisenberg Equation of motion. Let's write it down. Heisenberg Equation of motion. And we're going to discuss this as an essential tool to describe dynamics in quantum systems. This is important in the context of equilibrium and non-equilibrium Green's functions. These videos that you will often see in my channel. So then sometimes I will be referring to this video. So I suggest that you just take a look and see if you feel comfortable with it. Most people probably will, because this is a very basic tool. But for those who don't, then I have this review in this video. So now, what is the Heisenberg equation of motion? So then we can start saying that two very basic ways of representing operators in quantum mechanics are in the Schrödinger picture, to represent operator A in the Schrödinger picture, and in the Heisenberg picture we represent that operator but with a time dependence. And this is the basic difference. So in the Heisenberg picture, the time dependence is carried by operators. Okay? On the Schrödinger picture, the time dependence is carried in the wave function. Something like this: psi of r e to the minus I over h bar et. Okay, now what we want to do is, given a Hamiltonian, so that's quite important. So the Hamiltonian, which is what generates the physics of our system. So given a Hamiltonian H so the question we want to ask is, question, what is the dynamics of A sub ht, which in other words is, how does the operator A in the Heisenberg representation evolve? So then for that, what we're going to do is that we're going to write a representation for A sub h of t in the following way, which is nothing but the operator in the time independent representation. See, and we accompany that operator by to the right by the phase factor e to the minus a of I over h bar ht, and to the left to e to the I over h bar ht. Okay, so then this is the way we write the time representation of operators in the Heisenberg picture given a Hamiltonian. So this is given a Hamiltonian. Now there's not much we can do with this. So actually what we want to do is to derive a differential equation, in which case when we solve the differential equation we will get the dynamics of A sub ht. So that's what we want to do. To derive such a differential equation, what we do is just take the total derivative of A sub h which is equal to the total derivative of e to the I over h bar ht, the operator A in the Schrödinger picture, times e to the minus I over h bar ht. Then we have all ingredients to start our calculation, and we just take derivatives here. Just as a reminder, recall that this is just something to recall. If you take the derivative of the product of three things, let's say A, B, and C, this is A dot, so the derivative of the first times the second and the third, plus the first times the derivative of the second times the third, plus the first and the second times the derivative of the third. So this little formula will be enough to remind you how to calculate the derivative of operator A sub h. Okay, so then going back to that, what we have is the following. So the derivative of A sub h of t is equal to the derivative of the first one, okay, of this one, which is I over h bar, h times e to the I over h bar h t operator A sub s e to the minus I over h bar ht. Okay, now plus, now we take the derivative of the second one, which is this one. So again we write e to the I over h bar ht, partial derivative of operator A in the Schrödinger representation, times e to the minus I over h bar ht. And lastly, we take the derivative of the third term in the original equation, which is this one. This is negative, and since this Hamiltonian h in general will not commute with this operator A, so we cannot move the Hamiltonian to the left, but we can move it to the right, because the Hamiltonian will commute with this exponential, because will commute with itself. The exponential is just a series in the power series in the Hamiltonian, so you can commute with the exponential basically. So then what we have here is that to take that derivative, so we write first e to the I over h bar ht times the operator A in the Schrödinger representation times the derivative of this term, which is minus I over h bar h times e to the minus I over h bar h. And basically what I just said is that on the third line of this calculation, I can move this Hamiltonian h to the right, but I cannot move this to the left of operator A. That's forbidden, because in general A and h will not commute. So that's the thing. So then we have to, if we're going to move Hamiltonian h on the third line, we will have to move it to the right of the exponential, but not to the left of the operator in the Schrödinger picture. So then we do the following. Let's use some colors here. So then this is some factor that I have, which I will write I over h bar h. And do note that this part here is nothing but a sub h of t, so the representation that we started with. So then we write it down. Okay, so now in a different color, let's use purple. We will highlight the second line, and this second line, which is rather unimportant in our development, is nothing but the derivative, the partial derivative of operator A in the Schrödinger picture written in the Heisenberg representation. So what we will do is just to write that in the Heisenberg representation. So derivative of AS with respect to t, but in the Heisenberg representation. Okay. And the third line, which is a quite interesting line, let's check it out a little bit. Let's write it in black. What we can do is that we can move, since minus I over h bar is just a number, this one, so we can move it up front, and this Hamiltonian h, we can move it to the back. That's what we're going to do. So then we write minus I over h bar e to the I over h bar ht. See? As. What else? So I write e to the minus I over h bar ht, and here I write h. So what actually is this? So then this here is nothing but the representation we started with for h a sub ht. Okay, so then how is that going to look next in the next line? So it's going to look like this. Let me just elaborate a little bit. Let's use purple again to just close everything here. So then this so just one remark, that this term here in the middle usually is 0, because since a of s carries no explicit time dependence, then this is usually 0. But the Heisenberg equation of motion considers this term, so we will leave it there just for the meantime, but then we will work with the term from the very right and the term from the very left, which is this. So this is equal to I over h bar h times a sub h of t. Now we write this prefactor here, which is minus I over h bar, and then we write immediately after a sub h of t times the Hamiltonian, and we just add this, even though I have said that it's taken to be 0 in most cases, but let's leave it there for formality. Now what you can see here is that the second term is pretty much a commutation of the operator shown in the first term. So then we're going to write it in the following way. First, I over h bar, just some parentheses, h times a sub h of t minus a sub h of t h. Because this is a commutation operator, this thing here is called a commutator. And is written like this, with brackets, h a sub h of t. And this is an essential object in quantum mechanics. So you have to be familiar with this. There are ways to calculate that, and depending on the Hamiltonian, it's harder or it's easier, but we should always be familiar with this. Very important. And then, which is right here, plus the term that we said is less important, which is the time derivative of the operator in the Schrödinger picture, but written in the Heisenberg representation. Okay, so then given this, all of this calculation that we have, we can actually now proceed to write down some differential equation for operator a sub h of t, which is equal to I over h bar commutator between h, the Hamiltonian also has the hat, so then I didn't put the hat in the Hamiltonian, but the Hamiltonian is an operator, so just be aware of that the Hamiltonian has a hat. And this h here is not the Hamiltonian, is the h labeling the fact that the operator is written in the Heisenberg representation. That's all. So then so Hamiltonians have a hat, so then here this is the commutator between the Hamiltonian and operator a sub ht plus this time derivative here. Okay, so this is the Heisenberg equation of motion, and as such, you will find it in Wikipedia and all that stuff. Now, what can we do with this? So that's a good question. So then the first thing is to say that in all our videos so far, well, maybe in the future we will do something different, but so far we will have this as 0. So then the actual Heisenberg equation of motion that we will be using is dH t dt. It will be equal to I over h bar, and commutator of h and a sub h of t. Okay, this is the actual equation of motion that we will be using in our videos. So just become familiar with that, and become familiar with the fact that we will be seeing a lot of commutators in all our videos on quantum mechanics or condensed matter theory. When we let's say when we talk about molecules, there will always be commutators. When we talk about electrons, when we talk about vibrations in molecules, always there are commutators. So make sure that you are familiar with that if you want to keep on watching my videos, because it will be important. I will elaborate more on commutators later on. For the meantime, I just want to show you how to work with this. So then now, typically, since the Schrödinger equation, just recall that the Schrödinger equation is written in a time-dependent form like this. So nabla square, yeah, plus just some potential that depends on R times psi of R comma t. Okay, so then since this is the way we write Schrödinger equation, and here is Schrödinger equation, the wave function carries the time dependence, which means what does that mean? That we're in the Schrödinger picture. So then in the Heisenberg picture, sometimes people just by, I don't know, just by convention, they like to have the differential equation we have here, they like to have it in Schrödinger form, meaning that you have I h bar times some time derivative. So then in that case, we write this Heisenberg equation of motion like this. We multiply both sides by h bar, and then multiply both sides by I. See, so then we pick up I h bar dh of t dt, and here you pick up a minus sign due to that. So this is minus the commutator of h and a sub h of t. And when you have commutators with the minus sign up front, you just invert the elements in the commutator. So this is nothing but a sub h of t commutator with h. So this is the Heisenberg equation of motion written in Schrödinger-like form. Okay, and then now we will see something. So then now I want you to have a little bit of faith, because what I'm going to show you, you might not be very well acquainted with, but I can guarantee you that we will go through that. We will go through that in the videos. But for the meantime, let's grab some sample Hamiltonian of the following form. So this is just, let's say that this is some S scenario. In the case that the Hamiltonian that we have is just some energy E0 times some operator that we will call C with a dagger on top, followed by some C here. What this means is that C is an operator that by some complex operation, matrix operation on vectors represented in a Hilbert space, you remove one particle from a level with energy E0, and C dagger adds a particle to that level with energy 0. We will explain this later on, but the idea here is just to exemplify how to use Heisenberg's equation of motion. Okay, so then now what we have is that if we want to calculate the time derivative of operator C, how operator C evolves in time, then we do it in the following way. The derivative of C of t and this is equal then to the commutator between C and the Hamiltonian, which is just H. This is equal to the commutator then between C. We replace the Hamiltonian, which is E0 C dagger C, and this is equal to E0 C dagger C. Up to here everything should be okay, and now we have to start thinking about what I told you early on about the number of particles that this C removes a particle from an energy level E0, and that this C dagger adds that. So then we have to think, what is the nature of that particle? Is that particle a fermion? So C of t represents a fermion or represents a boson. Okay, so this we have to think very deeply. What is it? Is it an electron that is a fermion? Is it a photon that is a boson? Is it a single vibration mode that is a boson? Is it a neutron that is a fermion? So then this is what we have to think of, because the rules to calculate that commutator will be different depending on if it's a fermion or if it's a boson. Okay, and then now I can tell you this: the particles that are represented by these operators are in this case fermions. Okay, which means the following: if I have a Hamiltonian of this form, with 3 fermion operators, I have an identity that I want you to actually absorb, like you absorb water. Very important identity, which is the following: 3 in a commutator between a fermionic operator A and the product of 2 fermionic operators BC. This will be equal to what is called here, and this is a new concept then, what is called the anti-commutator between A and B times C, and minus B times the anti-commutator between A and C. So it turns out that commutators are more common or typical when we calculate stuff for bosons. When we calculate things for fermions, anti-commutators are more common, and the rule for anti-commutators is that the anti-commutator of A and B is A times B plus B times A. In contrast to commutators, which a commutator between A and B, as we saw earlier, is AB minus BA. Okay, so then now with this identity that I have shown up here, we are all set to simplify this. So then let's write it again in black. dc of t dt is equal to, of course, the commutator between c E0 c dagger c, which is equal to E0, the commutator between c and c, the product between c dagger and c. And with this identity, we already know that this commutator can be calculated using this rule. So then that's what we're going to do. So this is E0 parenthesis. So then the first we have the anti-commutator between c and c dagger, because the anti-commutator between the first one and the second one in that order, which is c dagger times c minus the anti-commutator minus the middle operator c dagger times the anti-commutator between c and c, because it's the anti-commutator between the first operator in the commutator and the last operator in the commutator. So that's what we have here. We close the parentheses here, and then it comes out that we have to use more rules from fermions. Rules for fermions. When you have anti-commutators, there is a rule that says that the only possibility by which you don't have a vanishing value of an anti-commutator is this one here. So this is equal to 1. Any other anti-commutator is equal to 0. So then this is equal to 0 as well. It's another rule. So then we write this E0 times 1 times c minus 0. That's what we have, and this is equal to nothing but then to E0 times c. That's the result, and then we have a differential equation, very easy to solve, because that was the idea of this exercise, to show you the Heisenberg equation of motion for something simple. So then I forgot the IH bar upstairs, so you have to forgive me here. Just a minute. Yes, here first on orange, this is IH bar. Sorry, that was in red. Let me erase this. In red it should be IH bar. Okay, here again, now in black, I forgot the IH bar. Oh my goodness, so sorry. IH bar here, and now in purple, of course there is an IH bar, how could I forget that? And this is equal to E0C. In other words, what we have here is the differential equation of the form C dot of t plus I over H bar C of t. Sorry, before we have E0 times C of t equal to 0. The solution for this is C of t, you can verify that very easy, equal to C of 0 times e to the minus I over H bar E0t. Okay, let's highlight it in black here a little bit. This is the solution to the differential equation, but it's not only the solution, it gives us the time evolution of operator C of t, like that. And if we want the time evolution of operator C dagger of t, we just complex conjugate everything to the right, because that's what the dagger does. So the dagger in a matrix first transposes the matrix and then conjugates the matrix. But in this case, for a scalar, just conjugates this time independent operator, and then it complex conjugates this phase factor e to the minus I over h bar e0t, which becomes e to the I over h bar e0t. Okay, then now you have done your first calculation using the Heisenberg equation of motion, and then you should feel proud about it, because this is a very important step to understand quantum mechanics, to calculate things. With this you will do a lot of stuff, and you will be able to plot many cool things showing quantum mechanics, showing the nature of particles at low dimension. So this is really important, this is really nice. So I hope that you have enjoyed this, and I'll see you in the next time. Okay, bye.